Hello. One of the most important skills you can learn early on in Chem 225 is drawing chemical structures. And not just drawing the structures, but realizing what the important information is to pull out of those structures. First place I want to start is an example with starting just with the molecular formula of a compound. So here we have C3H6 oxygen, small organic molecule, fairly typical molecular formula. The information in this molecular formula doesn't tell us much about a chemical, really doesn't tell us anything about a chemical. We need to draw structures, and we can form several structures from this one molecular formula. And those structures are, that are similar, but they're different, and so we call them isomers. First thing to do this, I'm going to review. We're going to take this molecular formula and convert it into Lewis structures. And from Lewis structures, we're going to convert that into bond line drawings. Probably the most important representation that we have in organic chemistry. So let's go ahead and start with some of the basic things we would do in drawing Lewis structures. And the first things we want to do is count valence electrons. These are the electrons that are involved in bonding, the electrons we're really interested in. So for C3H6 oxygen, we have 3 carbons. Each of those carbons have 4 valence electrons, so that we end up with a total of 12. With hydrogen, we have 6 hydrogens. Each of those hydrogens has 1 valence electron to give us another 6. And for that one oxygen atom, we end up with 6 valence electrons, since each oxygen atom would have 6. Add all these up, and we can see very easily we end up with 24 total valence electrons. These are the electrons that are going to be important in bonding and reactivity. We're going to need to know where all these are, even though we're going to not show all these once we get into bond line drawings. So that's the first step, kind of stage 1 with drawing Lewis structures. The next thing we need to do is find out, where do these 24 valence electrons go? And that's where we have to start putting the atoms together. And there's a couple different ways we can arrange the atoms. We have 3 carbons. It could be that each of those carbons are connected together. And the oxygen could be on the end. We could have same 3 carbons put together with the oxygen in the middle. We could also have a sequence where we have the oxygen in the middle of that carbon chain. These are 3 examples of possible ways we could start putting the atoms together. Now, the main thing to really keep in mind here is all of these atoms need to have an octet. So we're still going to really focus on the octet rule. Once we have gone through and built our possible skeletal structures, we need to make octets. We still have all of our hydrogen atoms here. So we've got to start deciding, where do we want to put these hydrogens. I'm going to start by putting them on the ends. And just start adding hydrogens on each side. And I'm going to continue this over here. Notice I didn't complete this. Partly, I've noticed with these valence electrons, if you start to go through and do a little more investigating, you find out we're going to have a multiple bond. And so I didn't want to just start saturating all our carbons. And we use that word saturating intentionally. Hydrocarbons that have all sigma bonds around the carbons we call saturated. So every one of these lines is a bond, we know that, but they're also a pair of electrons. And so I can count up these lines and say 1, 2, 3, 4, 5, 6. That's 6 pairs of electrons. 12 valence electrons, or half, have been used just in this drawing. I'm going to continue this. I'm going, for each of these examples, we have to get 6 hydrogens attached to these examples, so I'm going to attach all of the hydrogens onto carbons. But in the second example here, we already have all 6 of the hydrogens used. And in our bottom example, I'm going to go ahead and put 1 hydrogen in the middle carbon, 2 hydrogens on the end. That gives me some flexibility to make a pi bond someplace. Okay, on the top, let's go ahead and now start counting the number of valence electrons we've used as we've included all the atoms. So all of the atoms are used, all the carbons, all the hydrogens, all the oxygens in all 3 of these examples. So in this first example, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds, 9 pairs of electrons already in bonding. Well, 9 times 2 is 18 valence electrons. I still have 6 valence electrons left out of this 24. So 24 minus 18, got 6 left. We have to now take the remaining valence electrons, and the very first thing to do, make octets. And I'm going to start making octets around my oxygen atoms. We definitely don't want an oxygen atom to have an incomplete octet. And as I go through and start doing this, on the first 2 examples, I've used 3 pairs, that's 6 electrons. We're done. All 24 of those valence electrons have been used. There's no more valence electrons to show. I'm not completely done with the structures, because if you notice my carbon atom here and the carbon atom here, they don't have an octet. We still want to try to make octets. So what we end up doing is making a multiple bond. Going to take one of the lone pairs on the oxygen and share it with the carbon. Convert it into a bonding pair, in this case a pi bond. I'm going to do the same thing with our oxygen on our second structure. Make that a multiple bond. These 2 structures are good, complete Lewis structures, and they're all done. The bottom structure, if I go through and I count all my pairs of electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, that's only 22 valence electrons. I still have 2 left over to add in. I still have 2 carbons that have incomplete octets. I could just go ahead and put 2 of those electrons on one of the carbons, but then the other carbon is still going to have an incomplete octet. What I know by this is I'm going to add that as a pi bond, second bond of that double bond, and make octets around both of those carbons. All of the atoms have complete octets now, and they all have a 0 formal charge. As we go through and we really start looking at structures of molecules, we'll see examples where we'll have to develop formal charges for our Lewis structures, as well as develop resonance structures. I'm not going to do any of that with these examples right here. So this should be a nice review for you, looking at how we go from a molecular formula to a Lewis structure. Probably the most important skill, again, in organic chemistry, though, is taking these Lewis structures and converting them to bond line drawings. As you've probably gathered and noticed, it took quite a bit of time to draw out these structures, put all the hydrogens, put all the lone pairs in. As we get through or into the class, we're not going to want to spend that much time on these structures. We do want to know, okay, I want to know where all these lone pairs are. I want to know about these bonds. I want to know where the hydrogens are. But we're going to have some tricks to do a shorthand notation called bond line drawings that allow us to draw these structures very quickly without drawing in all this detailed information. We still want to know the information is there, but we're going to create shorthand notations. So how do we do that? Well, one of the nice things we have is we have this idea of what we call bends and ends. Bends and ends are what we use to signify carbon atoms when we just make lines. So for example, this top compound, I'm just going to draw this zigzag structure, And wherever there is a bend, right here on top, or an end, for example here on the side, these are carbon atoms. I'm no longer going to draw the C. I'm just going to know at every bend and end there's a carbon atom. That's not many bonds. Each one of these lines still represents a bond, but I'm also going to leave off all of the hydrogens. So as we go through here, we see in our top example, we have these 6 hydrogens attached to carbons. I'm not going to show those. I can get away with not showing those hydrogens because I know whenever I draw a carbon atom, it has to have 4 bonds. And if I don't draw 4 bonds to it, so for example, this carbon atom on the end over here, it only has 1 bond shown. There's only 1 line. I know that it has to have 4 bonds, so there has to be 3 hydrogens on this carbon right there. I just know that because I can add up to 4. So these 3 hydrogens we're not going to include. I know they're there. And that's kind of the important thing to keep understanding, remembering as we draw these line bonds. Now I still have the oxygen atom in here, and so I'm going to go ahead and put that oxygen right there. This is actually all I have to do to represent this structure. I don't have to put in lone pairs on the oxygen. Now you're not going to get marked wrong, or there's nothing wrong with putting those lone pairs in there. They're just not necessary. Might be a good idea at the beginning to include them so you just reinforces that you know that they're there. But this is all we have to include to represent this compound. There are 3 hydrogens on the carbon on the end here, 2 hydrogens on the carbon in the middle. The carbon in the middle has 2 lines to it, so I know there's 2 more. Not going to show them because I know they're just 2 hydrogens. This carbon on the end has 1, 2, 3 lines to it. I know there's 1 more. That 1 more is going to be hydrogen. Again, I don't have to show it. Now when we have this particular functional group, it's called an aldehyde, it is often that we show that hydrogen just to reinforce it. Just so that we can view this particular functional group, which we're going to study in Chapter 2, and recognize it a little more quickly. It doesn't have to be there. It's optional. Okay. Let's do the same thing for structure 2. Again, we still have 3 carbons. They're all in a row. That's representing those 3 carbons and all the hydrogens. Any other atom has to be shown. The only atoms that do not get drawn in are the carbons and the hydrogens. If there's an oxygen, a nitrogen, a halogen, we're going to draw those in. They have to show those. But we don't have to do them for this. This molecule's name is acetone. Propanone is an IUPAC name. That's all we're going to draw. We do know that there's 2 lone pairs on that oxygen. We're not going to have to draw them. It's important to know they're there. Finally, in the last one, we have a double bond between 2 carbons here. I'm going to draw that double bond. Both of those bonds get drawn. And then I have an oxygen with another carbon attached to it. This is all we have to draw. Again, there's 2 hydrogens attached to the carbon on the end here, as we see. There's 1 hydrogen attached here, and there are 3 hydrogens attached to this end carbon over here. This looks a little strange, especially as you first start to do this. Looks a little more normal if you put those hydrogens in and you put that C's in, but this is much faster to draw. We have to recognize, oh, you know what, the lone pairs are there. You don't have to draw them in. I'd recommend, as you start drawing these, you put those in just for reinforcement. Eventually, we're going to probably stop drawing those in. These are bond line drawings. There's a lot of information that you have to pull out of these bond line drawings. Concepts such as electronegativity and polarity play a big role in developing reactivity as we go forward, understanding resonance. Resonance is a very important concept in organic chemistry. These molecules all have resonance structures that we're eventually going to draw. Again, that goes back to really understanding how to do Lewis structures. We can also draw those resonance structures with the bond line drawings. So many concepts kind of get embedded in the shorthand notation of bond line drawings. Really recommend the faster you master this skill, you can look at these bond line drawings, understand what they mean, the easier it's going to be to get started in organic chemistry.